So let's resume our discussion of Mazur's chapter 12 on slide 23 of Phys 8 slides 12.pdf. And one major topic we're going to cover as one of our most fun applications of torque is static equilibrium. Now in real life, things live in a three-dimensional world, and we have three coordinates, x, y, and z. But normally we draw things on two-dimensional sheets of paper, so we will focus for now on static equilibrium in two dimensions. So then we have two coordinates, x and y, and the conditions for equilibrium, meaning that the object does not accelerate and it does not rotationally accelerate, are that all of the forces in the x-coordinate add to 0. You have to assign the proper sign to each force so that they can balance each other with canceling signs. All of the forces in y sum to 0, and all of the torques sum to 0. You have to choose a sign convention. Our usual sign convention is counterclockwise is positive, clockwise is negative, and you add up torques about some chosen axis. Nothing is really rotating in these problems, so the choice of axis requires a little bit of ingenuity, and we will see from examples often the best choice of axis is such that the line of action of a force whose value you don't care about passes through the chosen axis, so that you get equations as a result that simply do not depend upon the force that you don't care about. Here's a question that brings us back to the hands-on exercise we did in the very first day of class. If you have a beam supported on two columns asymmetrically like this, then which column supports more of the beam's weight? And in a configuration like this, if you tried it on the first day of class, you probably found that this right-hand column supported more of the weight and this left-hand column supported less of the weight. And the key to understanding that was that this column is farther away from the center of mass and this column is closer to the center of mass. And I suggested that you use the analogy of a seesaw and imagine two kids on a seesaw at different distances and imagining how the two kids' weights could differ in order to get them to balance the seesaw at these two locations. Now that we know about torque, we can see directly why the seesaw metaphor makes perfect sense. So after annotating our diagram, let's analyze this beam configuration, and then we can go back and look at the demonstration from the first day of class using two scales. So I annotated this diagram. So here is the center of mass of the beam, and I have the gravitational force pointing downward. And then here are the two contact forces on the left by column 1, on the right by column 2, and then I indicated the relevant dimensions up here, which are the horizontal distances from the center of mass to the point of contact of column 2 and of column 1. It's usually easier to redraw a diagram that just picks out the object of interest. In this case, we're interested in forces and torques acting on the beam, so we just draw the beam and we label it beam. This diagram will be called an extended free body diagram, EFBD. You want to include on the extended free body diagram usually an indication of the center of mass of the object, all of the forces acting on the object, and in this case you actually want to be sure to indicate the correct line of action of each force. So that shows the point of application of the force and the direction of the force. In the case of the gravitational force, we treat it as if its effect were entirely concentrated at the center of mass of the beam. We draw an arrow passing through the point of application of the force, which is the center of mass or center of gravity of the beam, and pointing downward. We label it the gravitational force by Earth on the beam, and then we know its magnitude is mg. Here we draw the contact force by column 1 on the beam, and we're just calling that F1 for short, and it's convenient in this case to make the tip of the arrow indicate the point of contact. Over here we have the contact force exerted by column 2 on the beam. So it points upward. This points upward. They're contact forces, normal forces. And we label this F2 for short. And then we'll see in a moment why we want to indicate this distance. Since these are vertical forces, we'll be interested in the horizontal distance between the center of mass and F2 and between the center of mass and the line of action of F1. How do we say that the forces sum to 0 in the y coordinate? I like to write up minus down. It often helps to write your axis convention on the diagram somewhere. Up minus down would be F1 plus F2 minus mg equals 0. That makes sense. The two upward forces exerted by the two columns on the beam must sum to the weight of the beam. Now actually, 0 equals the sum of forces in x doesn't tell us anything very interesting. It just tells us 0 equals 0 in this case because there are no horizontal forces. Now the trick here is, what is a good choice of rotation axis? And what is a good choice of rotation axis depends on what forces you're trying to solve for. But in this case, an excellent choice of rotation axis is the center of mass of the beam itself. So we'll say 0 is the sum counterclockwise, and sometimes it helps to say about the COM. Sometimes you can indicate your rotation axis. You might have a point labeled P of the torques. And now the convention here is anti-clockwise minus clockwise, and we're using the center of mass of the beam as our pivot. The gravity force has a line of action which points directly through the pivot, so it contributes a torque of 0 because the lever arm is 0. And this is a useful fact to bear in mind in the future. You often want to choose the pivot so that a force that you don't care about has a line of action that passes through that pivot. So let's do counterclockwise. F2 is a counterclockwise sense about this pivot, and then minus clockwise. So we'll do the torque due to F2 first, and then the torque due to F1. Remember, a torque is perpendicular distance, that's the lever arm, times the force. At least that's usually the most convenient expression for torque. So since this is a vertical force, we want horizontal distance to be perpendicular to the line of action of the force. So we have the horizontal distance is R2, and then the force is F2. That's anti-clockwise. Now clockwise has a minus sign, so the horizontal distance from the pivot to the line of action of F1 is R1, and then the force is F1. So we really want to measure this horizontal distance to the line of action of this vertical force, and we want to measure this horizontal distance to the line of action of this vertical force. But it's often convenient to make your annotations where they don't get in the way of the diagram. So with some practice, you figure out where to annotate so that your annotations are as legible as possible. This last line immediately tells us that R1 F1 equals R2 F2, or equivalently that F1 over F2 equals R2 over R1. And you might remember on the first day of class we found that the two forces had to add up to the weight of the beam we were supporting, and that the ratio of the two forces was the reciprocal of the ratio of the two distances from the center of mass. And now torque lets us explain that observation from the first day of class. To solve this all the way through, we can take this second equation and solve it for F2 so that we can eliminate F2. So that gives us F2 is R1 over R2 times F1. Then we can take this equation and put mg on the right hand side. We get F1 plus F2 equals mg. Then here's F1. We can substitute our value for F2 over here. Then we want to combine these two terms, so we can multiply the first term by R2 over R2, which is just 1. Now we have a common denominator here, so we can call this R1 plus R2 over R2 times F1 equals mg, which we can then solve for F1. F1 equals R2 over R1 plus R2 times mg, since this R2 moved up here and this R1 plus R2 moved down here. By analogy, we could do the same steps and get F2 equals R1 over R1 plus R2 times mg. Then to go back to one example from the first day of class, if one support, let's say support number 1 is 2 units away from the center, and support number 2 is 1 unit away from the center, then the force held by the first support will be 1 over 3, 1/3 of the total weight, and the force held by the second support will be 2 over 3 is 2/3 of the total weight. One thing you might wonder is, what if you picked a different axis? Well, it turns out that depending on what you're most interested in, sometimes it is really convenient to pick a different axis. For example, suppose we wanted to find a shortcut that would get us directly to this equation without so much algebra. Notice that this result contains F1 and it doesn't contain F2. So we were looking for an expression that eliminates F2. One way to eliminate F2 is to make the pivot go through F2. Let's see what happens if we make the pivot go through F2. So let's pivot about a point through which the line of action for F2 passes. So I've drawn my pivot here, just to the right of the center of mass by a distance R2. Now notice that the weight of the beam. The gravitational force is a counterclockwise torque, so that's positive. And notice that F1 is clockwise, so that's negative. So we will write perpendicular distance to the gravity force is R2, and then minus R1 plus R2 F1 equals 0. We can then immediately solve this for F1. We get F1 equals R2 over R1 plus R2 mg, which is the same result we got over here, but we had to do much more work to get it over here. Once you get good at this, by choosing the right pivot, you can save yourself some algebra. So you only get 3 equations worth of information for equilibrium in a plane. So you really only have 3 independent equations. So if you choose a different pivot, you won't get any new information. You'll just get something that would have come out of a linear combination of the other 2 equations. But sometimes you can get much more directly to the result you want by clever choice of a pivot. There are also some special cases where you can use 2 pivot equations plus 1 force equation, but just file that fact in the back of your mind. Almost always we will use 1 force equation in X, 1 force equation in Y, and 1 torque equation with carefully chosen pivot. And again, if you feel that you don't know how to make a clever choice of pivot, the only thing that's lost is you have to do a bit more algebra to get the final answer. So the only thing that a clever choice of pivot typically does for you is save you a little bit of math. A beam of mass big M and length big L is attached to a wall by a hinge. A sign of mass little m hangs from the end of the beam. The end of the beam is supported by a cable at a 30-degree angle, theta equals 30 degrees, with respect to the horizontal beam, which is anchored to the wall above the hinge. What forces act on the beam? Draw an extended free body diagram. Find the cable tension T. Find the reaction forces, Fx and Fy, exerted by the hinge on the beam. What 3 equations can we write for the beam? As the problem suggests, the first step in such problems is often to draw an extended free body diagram. So let's do that now. Let's start by drawing the beam, labeling it as a beam, and indicating where its center of mass is. Now let's figure out what forces act on the beam. Usually our first choice is gravity. The line of action of gravity passes through the center of mass of the beam. Gravitational force by Earth on the beam is big M times little g. This hinge is capable of exerting both horizontal and vertical forces on the beam. So let's draw both of those forces. You can give it a long textbook style name like contact force by the pivot on the beam, y component, contact force by the pivot on the beam, x component, though in this case I would probably give it a shortcut name, either fx and fy, or sometimes you might call it px and py since it is exerted by the pivot at point P. So it'll be pretty common later if forces are happening at some point P to call them px and py, or if they're happening at some point A to call them ax and ay. But for now, let's call this fx and fy. We need 2 more forces. First is the contact force by the sign, really the cable that holds the sign on the beam. Let's just call that the contact force by the sign on the beam. So there's F, contact by the sign on the beam, and that's little m g. You know that as long as the sign is not accelerating, that this force will just equal the weight of the sign. Although it is an interesting fact that if this sign were accelerating, that force could be different. But usually in static equilibrium, we're treating everything as static. Then we have the tension. So this is, you could call it the contact force by the cable on the beam, but really it's just the tension T, and it helps to indicate this angle theta, which we're told is 30 degrees. Let's do one more thing at this stage. Let's decompose the tension force into x and y components, which will make our equation writing easier. Okay, we have horizontal forces Fx and T cosine theta. We have vertical forces Fy, mg, little mg, and T sine theta. Now in this problem, there is a natural choice of pivot at this point P. We could use other pivots, but Since we have such a natural pivot, let's do that. The next step is to figure out what three equations we can write for the beam using our extended free body diagram. How do we write the statement that the sum of the horizontal forces acting on the beam equals 0? And remember, our usual sign convention is to say plus, minus, minus. So right minus left. It seems as if acting to the right, we have at least the way we've drawn it, the reaction force, the force exerted by the pivot in the horizontal direction. Since we drew it to the right, we could have drawn it to the left and then we would just get the same answer with a minus sign. So we have fx minus, and then to the left is t cosine theta. Now, one thing I didn't plan, my convention is to say the sum of the forces in x, just to write it as sum fx. So this use of f sub x is completely different from this use of f sub x, which actually represents this horizontal force up here. I hope that's okay. So I think I like answer C, Charlie over here, f sub x exerted by the pivot on the beam minus t cosine theta equals 0. Next, how do we write that the sum of vertical forces acting on the beam equals 0? And the convention I like to follow is upward minus downward forces. Upward, we have this vertical support force exerted by the pivot. We actually don't know for certain which way it will point, but we guess upward, so we'll stick with the way we drew it. And then we have the vertical component of the cable tension. That's all the up forces. Then we have two down forces. We have the weight of the beam itself, and then we have the contact force by the sign, which basically equals the weight of the sign, assuming that the sign itself is not accelerating. So let's see which of our candidate answers seems to match this. I think I like answer F, foxtrot, pivot force in the y direction plus t sine theta minus big mg minus little mg equals 0. So there we go. I think I like answer F. So we've been recapitulating all along. The beam has mass big M and length big L. The sign has mass little m. The cable is at an angle theta with respect to the horizontal. And the hinge exerts a rightward force F sub x and an upward force F sub y on the beam. And again, if we guessed wrong about the directions of the hinge forces, we would just get a negative answer. So you just want to write the equations corresponding to the way you drew the arrow. And if you get a negative number, then you know you drew the arrow the wrong way. How do we write the sum of the torques about the hinge equals 0? And again, maybe we could have chosen a different pivot, but we chose the hinge as our pivot. So using the hinge as our pivot, and I've drawn this as P. So the sum of torques counterclockwise minus clockwise about the point I've drawn here as P, the letter tau for torques. So let's go through. So there's 0 torque from the hinge force in the horizontal direction because our pivot is the hinge. There's 0 torque from the hinge force in the y direction because the hinge is our pivot. And let's try to do counterclockwise minus clockwise. We'll go through the counterclockwise ones first. So this would be clockwise, this would be clockwise. Now the horizontal component of the tension is also drawn in such a way that, assuming that we neglect the thickness of the beam, then this torque is 0 because this is a horizontal force, so it would need a vertical displacement. So if we knew precisely the thickness of this beam, then we could write a term for this horizontal force times the vertical displacement with respect to our pivot. But since we didn't label any dimension for the thickness of this beam, I think we're treating it as a beam whose thickness is negligible compared to other dimensions in the problem. So I think for our purposes we can say that the line of action of this horizontal component of the tension just passes right through the pivot. Whether it did or not, I think would depend in detail on how we attach this cable. So I drew it as if we attached the cable to the very tip of the beam. Maybe in fact we attached the cable to a little hole drilled through the center here. In that case, even if we knew the thickness of this beam, the line of action would pass directly through the pivot, since the pivot also passes right through the vertical center of the beam. One way or another, this horizontal component of tension either has a line of action that passes directly through our pivot or has a line of action that passes through our pivot with a vertical displacement that seems to be so small that we're neglecting it. So there's 0 contribution from t cosine theta. T sine theta, however, this would be a counterclockwise torque. So we'll say t sine theta, and then this is a vertical force. The appropriate displacement is a horizontal displacement, and that seems to be the entire length of the beam. So the first term we get here is the length of the beam times t sine theta with a plus sign because it's counterclockwise. That's it for counterclockwise contributions. Now for clockwise contributions, we have the weight of the beam itself, and it has a lever arm of half the length of the beam. So there's L over 2 for the lever arm, the horizontal distance from the pivot to the point of application of the force, to the line of action of this gravitational force acting on the beam. So this is a vertical force. The gravitational force is a vertical force, so we want the horizontal displacement from the pivot to get the lever arm. So that's L over 2, 1/2 the length of the beam. Then we have the weight of the sine. The weight of the sine has a line of action that passes through the end of the beam. So this is the entire length of the beam. This is a vertical force. We want the horizontal displacement to go with the vertical force, and the appropriate horizontal distance is the entire length of the beam. So that's all the terms we have. Big L t sine theta minus L over 2 mg capital M minus L lowercase mg equals 0. So that seems to be answer F, foxtrot. I didn't use my positive minus negative convention when I wrote these answers down. So the positive term is LT sine theta. We have that same positive term here. The negative terms are minus L over 2 mg and minus L little mg. So I think I like answer F, foxtrot. Next, let's solve this system of equations so we can get the tension. We have 3 unknowns. By the way, in statics in a plane, you only get 3 equations, so there are only 3 unknowns you can solve for. So you have to make sure you don't have more than 3 unknowns. So our 3 unknowns are this horizontal force exerted by the hinge on the beam, this vertical force exerted by the hinge on the beam, and the tension. Why does the tension count as only one force, whereas the force exerted by the hinge counts as 2 forces? And it's because we don't know how this force exerted by the hinge is divided between horizontal and vertical components. We have no idea what the ratio of horizontal to vertical parts is until we solve the problem. By contrast, we are told what the angle is for the cable. The force exerted by the cable has to point along the axis of the cable. So since we know the direction, there's only one component here that we don't know. Since we don't know this direction, we have 2 unknown components. So that's 1, 2, 3 unknowns. Now, this third equation, the torque equation, which we might also call the moment equation, engineers and architects tend to refer to torques as moments of forces. That's like you take the moments of a distribution, like the mean is the first moment, the variance is the second moment of a distribution. So in mathematical terms, the torque is the first moment of force because you're multiplying each force by its corresponding distance from the pivot. So you can call them moments if you like. If you take an architectural structures course, you will call them moments there. But for now, we're calling them torques. So it seems as if the only unknown in this third equation is the tension. So this lets us solve directly for the tension. Okay, that gives us the tension is big mg over 2 plus little mg, all of that divided by sine theta. By the way, this divided by sine theta is kind of an interesting fact. It often turns out that if you apply a force at a small angle, that force has to become very big. So notice, if the cable were oriented vertically, the tension would be only equal to big mg over 2 plus little mg. If you orient the cable at a very small angle with respect to the horizontal, well, it's only the vertical part of that tension which is doing anything useful to support the weight. So we have sine theta in the denominator. So the smaller the angle of that cable with respect to the horizontal, the more difficult its job is. Now that we have the tension, we can easily figure out the horizontal force exerted by the hinge. So we take this tension times cosine theta. So this is cosine theta divided by sine theta. But you know that sine theta divided by cosine theta just equals tan theta. So in fact, this is just like writing tan theta downstairs. Then finally, let's solve for the vertical force exerted by the hinge on the beam. So moving F sub y over to the other side, we have t sine theta minus the 2 weights. Keeping F sub y on the left side, moving everything else over to the right, we have the sum of the 2 weights minus t sine theta. So that gives us the vertical force exerted by the hinge on the beam is 1/2 the weight of the beam itself, and it seems not to depend on the sine. That's kind of an interesting result. The reason it doesn't depend on the sine is that the sign is hanging directly below this cable. So it turns out that the weight of the sign is carried entirely by the vertical part of the cable and not by the hinge on the other side. So here again is our solution. The cable tension is half the weight of the beam plus all of the weight of the sign, all of that divided by sine theta. The vertical force exerted by the hinge on the beam is just half the weight of the beam and nothing else. And that's kind of interesting. It's a consequence of the fact that the sign is supported just below the cable. And then the horizontal force exerted by the hinge on the beam is half the weight of the beam plus all of the weight of the sign and then divided by tan theta. So the smaller you make this angle with respect to the horizontal, the bigger the horizontal force is that the hinge has to exert to oppose the horizontal part of the tension in the cable. Okay, next let's build a highly simplified model of an arch. I think this model, as simple as it is, does exhibit some interesting features of an arch. So the way we've designed our arch, this is a wooden plank on the left side. This is an identical wooden plank on the right side. They are held together by a hinge. And then at the bottom, the buttressing force that keeps the sides from spreading out is the tension in this string. In fact, the string is a little piece of chain in real life. And then we have the two sides of the arch rest on little skateboards. The reason we rest them on little skateboards is so that we're exerting only a vertical force here, not a horizontal force. That then allows us to measure the horizontal force that is necessary to buttress the sides of the arch so that the arch doesn't just fall down. You can imagine if this little piece of chain were not present, but we have the arch sitting on these two skateboards, I think you can just kind of envision, it'd be like walking on a sheet of sheer ice. It's a bit like my dog if he doesn't kind of keep his legs close together when he's on a really slippery floor. His paws just tend to spread out a little bit and leave him splayed on the ground. So this arch would tend to flatten out if we didn't have some kind of a horizontal buttressing force keeping the two sides close together. So naturally this thing just sort of wants to flatten out. So the advantage of using a separate piece of chain here is that we can put a force scale in the middle of this piece of chain and we can measure how big the tension is that holds the two sides together, and then we can compare that with our calculation. By the way, when we start drawing more little elements of structures, we will see things that look like roller supports. The whole idea of a roller support is that it can exert a force. In this case, if it's a roller sitting on a horizontal surface, then it exerts a vertical force. It exerts zero horizontal force because you assume it's a frictionless wheel or frictionless roller, like a frictionless roller skate. A pin or a hinge, by contrast, can exert a force in two different directions. So actually, encapsulated in this really simplified model of an arch, we have some things that will repeat many times later in the course. We have the idea of a horizontal buttressing force that you've seen when you studied Gothic cathedrals, for example. We have the idea of a hinge or a pin connection, which can exert a force, but it cannot exert a torque. So it does not resist rotation about this point, but it can exert a force either this way or this way. And then we have the idea of a roller support, quite literally in the form of a roller skate or skateboard in this case, which by design exerts a force only in one direction, but not in the perpendicular direction. And then I think we're also going to see that for a given weight of these side pieces of the arch, if we make this arch tall and thin, we do not need a very big horizontal buttressing force. But if we make the arch sort of short and wide, then we do need quite a large horizontal buttressing force. So that'll be sort of an interesting outcome. And we measure that angle, whether it is short and wide or tall and thin, by this angle theta. So this angle theta between the horizontal and the diagonal, in other words, between the horizontal chain and the diagonal wooden plank, we call theta. So a small value of theta would be a short, wide arch. A large value of theta would be a tall, thin arch. Now, I told you a moment ago that the equations for static equilibrium in a plane can solve for only 3 unknowns, because you only have 3 equations: forces horizontally, forces vertically, and torques about some pivot. Yet we have here in this diagram 1 unknown tension, 2 unknown vertical forces, so that's 3 total, and then 2 forces that can be exerted by this hinge. So we have 5 total unknowns, but we only have 3 equations. So somehow we need to cheat so that we can make this problem solvable using static equilibrium in a plane. The way we're going to cheat is to exploit the symmetry of the situation. So we are actually going to draw a free body diagram, not for the whole arch, but just for 1/2 of the arch, and we will exploit the symmetry. Another trick you'll see us use when we exploit this symmetry is that it is possible for the left and right sides of this arch to be pushing toward each other or away from one another. So a horizontal force by this hinge is certainly possible. Not just possible, but really mandatory, because the horizontal force by this hinge will somehow oppose this tension. But we can argue by symmetry that there's no vertical force exerted by one side of this arch on the other. For example, imagine that the right side is pushing down on the left side. Well, then by symmetry you would think that the left side should be pushing down on the right side. Or suppose the right side is pushing up on the left side. Well, by symmetry then you should think that the left side is pushing up on the right side. So I claim that by symmetry there is no reason that one side of this arch should be pushing up or down on the other, because if you do a mirror image, you see if this is pushing up on this and then this is pushing down on the other part, if you then reflected that in a mirror, you would change the signs. So I claim that the mirror symmetry of the situation argues that there must be 0 vertical force exerted by the hinge. There can be a horizontal force, because suppose the left side is pushing against the right side. Well, then the right side is pushing against the left side, and when you make a mirror image, that doesn't change. That's fine. But if you had the left side pushing up on the right side, when you make a mirror image, that would flip the sign. So the only way that you can have the mirror image be the same as the original is if the vertical force is 0. That's a little bit of a sleight of hand, but it's a valid sleight of hand as long as we really do build this perfectly symmetrically, and it's a sleight of hand that allows us to solve the problem. So we will do what we need to do to solve the problem. So often the essence of physics is to reduce a complicated problem to a similar but simplified problem that is easier to analyze. So that's what we're doing in this model of an arch. So one piece of information we need to record here before we move on is that the weight of each plank, in other words the weight of each side of the arch, is 20 newtons. So each wooden plank that constitutes one side of the arch has a mass of about 2 kilograms. So again, we're using a cable or a little piece of chain to hold the bottom together, because that allows us to put a force scale, a little Newton scale, in the middle so that we can measure the tension and explicitly check it against our model. And again, we're going to exploit mirror symmetry and analyze just one side of the arch. So if we draw an extended free body diagram for the right-hand plank, what forces act and where do they act? So let's figure out the forces. Let's figure out the points of application of those forces, and let's figure out the line of action of each force that acts on the right-hand side of the arch. And we will do that as part of drawing an extended free body diagram for the right-hand plank. So here is the right-hand board or plank. I guess I'll call it B for board. We could have called it P for plank. Let's call it B for board. And then we can call this H for hinge. So the first force is the gravitational force by Earth on the board, which just equals mg. The next force is the tension force, the contact force exerted by the cable. So I'm going to say this is the tension T, which is the contact force exerted by the chain or the cable on the board, and it's horizontal. The next force is the vertical contact force. We could call it the normal force, since we're sort of accustomed to the vertical force exerted by the floor on something being the normal force. So let's call this the normal force exerted by the floor. I mean, it's the roller skate, but let's call it the floor on the board. And we don't know how big that is, so maybe we'll just call this F normal for short. And finally, we have the contact force exerted by the hinge on the board, and we said that there can be a non-zero x component. We argued that it doesn't make sense by mirror symmetry for there to be a non-zero y component, and that's a good thing because that would be then 4 unknowns. We only have 3 equations. So let's just call this the force exerted by the hinge. Let's call it the force in x exerted by the hinge. Then in order to draw torques, we will need to figure out dimensions. So let's call the length of this board L. We can compare with the extended free body diagram I already drew on slide 34. I think it has the same features. Tension acting to the left at the bottom corner of the board. Normal force acting upward at that same bottom corner of the board. The horizontal force exerted by the hinge, also known as the pin, at the upper corner of the board. And then gravity acting directly downward at the center of mass, also known as center of gravity of the board, and then the length L of the board. How many unknown variables is it possible to determine using the equations for static equilibrium in a plane? Well, we have one equation for force horizontally, one equation for force vertically, and one equation for torque. So that's 3. We have 3 equations. Using those 3 equations, we can determine 3 unknowns. So static equilibrium lets us write down 3 equations for a given object. And in this case, I wrote the third equation as the sum of the moments about the z-axis equals 0. Normally, I would just say the sum of the torques equals 0, and I would indicate the direction of rotation. And I might indicate the point that we're using as the pivot. I'm trying to be a little more engineer or architect-like in writing this down this time. So let's start with the torques, also known as the moments. And let's evaluate our moments about the hinge, which I'll call H, the top corner of the board. To add up the torques about this hinge H, let's do counterclockwise minus clockwise. So any force that is applied up here at the hinge has a line of action that passes right through the rotation axis and therefore has 0 lever arm. So we don't have any contribution from this force exerted by the hinge. How about the tension? So the tension would tend to be clockwise. The normal force would tend to be counterclockwise. And then about this pivot, gravity would tend to be clockwise. So let's do normal force minus the other 2. What is the lever arm for the normal force? Well, the normal force is a vertical force, so we want the horizontal distance from the pivot, since it's a vertical force. The horizontal distance from the pivot to the point of application of the normal force, which could also be said as the horizontal distance from the pivot to the line of action of the normal force, is L cosine theta. So we have L cosine theta times the normal force. And we could draw the triangle just to argue that. So it seems as if adjacent over hypotenuse. So adjacent over hypotenuse is this lever arm that we want divided by L, that's cosine theta. So the lever arm that we want is L times cosine theta. So first term, L cosine theta times normal force. Then let's do the tension. What is the lever arm for the tension? Well, the tension is a horizontal force, so we want the vertical displacement for the lever arm. So that must be L sine theta. And we can see that. So in this case, we have L r perp. So the orange r perp over L is opposite over hypotenuse is sine theta. So for the orange case, in the orange case, r perpendicular is L sine theta, opposite over hypotenuse. Then we have the gravity force. So this is a vertical force, so we want the horizontal displacement. So this horizontal displacement is just 1/2 of this horizontal displacement. So the normal force was a vertical force whose line of action was L cosine theta away, and the gravity force, the weight of the plank itself, of the board itself, is a vertical force whose line of action is a horizontal distance L 1/2 L cosine theta away. So here's our torque equation. 0 equals L cosine theta F normal minus L sine theta tension minus L over 2 cosine theta mg. So I think that turns out to be answer A, alpha over here, minus mg L over 2 cosine theta plus F normal L cosine theta minus LT sine theta equals 0. Next, let's try the sum of the horizontal forces acting on the beam. So I do right minus left usually by convention. To the right we have the horizontal force exerted by the hinge, and to the left we have the tension. So that's pretty easy. We just get that the tension is the same as the horizontal force exerted by the hinge. Same magnitude, opposite direction. Next, let's try the vertical forces. So I usually do up minus down. In the up direction, we have the normal force. In the down direction, we have just the weight, and that's it. That tells us that the normal force just equals the weight. So let's use these last two equations to eliminate the normal force and eliminate the force exerted by the hinge, so we'll just be left in terms of the tension and the weight. Now we can solve for the tension, so we'll move this term over to the left side. These two terms can stay on the right side. Then we can cancel an L everywhere, and we can combine these two terms since one is just half the other with a minus sign. Then we can divide both sides by sine theta, and the result we get is the tension is mg over 2 tan theta, where m is the mass of one of these boards. So the smaller we make theta, which means that the arch is more short and wide, the bigger the tension we need to hold it together. If we make the arch tall and thin with the same mass, then we need a smaller horizontal force to hold it together. And then you can also see that the tension exerted by the cable in the middle just opposes the kind of compressive force. So a real arch, well, a real dome has a kind of compression ring at the top center. Now let's see how this calculated result compares with our model that we built. So mg is 20 newtons, so we should have a tension of 10 newtons divided by tan theta. So plugging in a weight of 20 newtons for one board, we get that the tension in the cable that holds the arch together horizontally should be 10 newtons divided by tan theta, where this theta is measured with respect to the horizontal. So let's go see how that worked out. Welcome to my basement pool table. Normally my dad beats me on the weekends, but I had a lucky break last weekend. This is our homemade arch. Here's a little skateboard. Here's a little skateboard. The idea then is that the floor can exert a vertical force, but not a significant horizontal force on each board of the arch. Here's one board. Here's the other board. And we have a couple of wire ties used as hinges. So this basically forms a pin support between the two boards of the arch. This string with the Newton scale in the middle provides the buttressing force that holds the two sides together. Without the buttressing force, the arch would just flatten out on the table. And then the whole point is we want to see how big this buttressing force is as a function of this angle from the horizontal up to this board. And we calculated on the board earlier that given that the weight of each one of these two boards is 20 newtons, so the weight of the two boards together is 40 newtons. So the weight of one board is 20 newtons. And we worked out then that the force we expect to be read by the Newton scale here is 10 newtons divided by the tangent of theta. The first value we're using for theta is 45 degrees. The tangent of 45 degrees is 1, so we expect 10 newtons. Amazingly, we read 10 newtons here on the scale. To show you this is 45 degrees, well, to show you how I know it's 45 degrees, each one of these two boards is 48 inches long. We're using these old-fashioned units called inches. And this length, in other words, half the width of the base of the arch, divided by 48 inches should equal the cosine of theta. So that's equivalent to saying that half of the total base of the arch divided by 48 inches should equal the cosine theta. And I've checked that the total base of the arch from one end to the other is about 68 inches, and my calculation says for 45 degrees it should be 67.9 inches. So I'd say this is pretty close to 45 degrees. By the way, the results agree with my pre-calculated results from slide 43. You could also ask yourself, how would the result change if we suspended a mass from this point at the hinge? So if we suspended some mass big mg from the hinge. So since we used little m for this, let's use big M for this. How would that change the final result? I guess if you were going to do that, you would suspend from a cable here some weight, some mass big M. So then you would have big mg applied here. And then by symmetry, we're analyzing only half of the arch. So I guess you would put half of the weight here since the other half belongs to the mirror image. So that would be big mg over 2. Because the point of application of this force is right at the hinge, or better yet, because the line of action of this force passes through the hinge, which was our pivot, it would not change the torque equation, and it would not change the horizontal force equation, but it would change the vertical force equation. So instead of little mg, we would have little mg plus big mg over 2 to balance the normal force. And then I guess we could just fill in the rest of the results. So I don't think I want to go ahead and do that here. I think I might leave it as a homework problem. Or if you're feeling really ambitious, maybe it could be an extra credit problem. But I think I might turn it into a homework problem to ask what would happen if we suspended an extra mass, big M, from the hinge here. How would that affect the tension? I think if you worked it out, you would get that the new value for the tension is big M plus little m times g over 2 tan theta. But you're going to have to check me on it. Yeah, so I think that's what the new answer would probably be, but you should check to be sure. This is about the widest I can make this arch and still fit on the ping pong cover of my basement pool table. The full span of the base of the arch is about 84 inches, and then the length of one board here is 48 inches. Half of this full width, so the half width, divided by the hypotenuse, which is the length of one board, is the cosine of this angle with respect to the horizontal. So putting in the numbers, I get that the angle right now between the horizontal and this diagonal is about 29 degrees. And the force that I expect is 10 newtons divided by the tangent of this angle. We worked that out because the two pieces together weigh 40 newtons. So one piece weighs 20 newtons. And we worked out 10 newtons divided by tan theta for the expected string tension, the expected necessary buttressing force. I expect 18.1 newtons. I see right about 18 newtons. That's probably a little better than I deserve. Let me add 400 grams at the center. So that should be, so that's 0.4 kilograms. That's 4 newtons. So then I expect 2 newtons divided by tan theta. 2 newtons divided by the tangent of 29 degrees should be about 3.6 newtons. So I think I expect this number to go up by about 3.6 newtons. So I think that should bring it up to just below 22. It does seem to go up to just below 22. That's not bad. Now I set the full width of the base to be about 68 inches, and according to my calculation, this should be pretty close to 45 degrees. Yeah, so a 68-inch full width of the base should give me very close to a 45 degree angle here. So then I expect 10 newtons divided by the tangent of 45 degrees. The tangent of 45 degrees is 1, so I expect the scale to read 10 newtons. The scale, in fact, reads, about 9 newtons. 9.5 newtons. So that's not too bad. Then, if I add 10 newtons of force to this point at the apex, I expect the reading to increase by 5 newtons. Let's see how that works. But it should be 10 newtons divided by 2 divided by tan theta. So that should be 5 newtons divided by tangent of 45 degrees is just 5 newtons. So it's a 5 newton increase from what we see here. Depending on how exactly I wiggle it, I probably see somewhere between a 4 and 6 newton increase. So that seems pretty good. Just for fun, I can add an additional 10 newtons, so now it should be pretty close to 20 newtons total that I read on the scale. Yeah, depending on how jiggle things. There's a little bit of friction, so every time I jiggle it, I think the friction does something a little bit different. So I get somewhere between 19 and 21 newtons total, depending on the luck of sort of wiggling and releasing things. So I see here I got 19, here I got 21, here I got 20 and a half. Okay, that's 20. So that seems pretty compatible with our model. Okay, now I've reoriented so that the full span, the full width of the base is about 50 inches. So that gives me, this angle theta is about 58 or 59 degrees, a little closer to 59. So for 59 degrees, I expect a force of 6.1 newtons. I see about 5.6 newtons. Now I see about 5.0. Now I see about 5.5. Now let me add an additional 2 kilograms of mass here. So that should be 20 more newtons down. So adding 2 kilograms, that's adding 20 newtons up here, should increase the scale reading by 20 newtons divided by 2 tan theta. That's another 10 newtons divided by tan 59 degrees. So it should double our reading from about 6 newtons to about 12 newtons total. Let's see how that works. That's not bad, you see? So we see about 12 newtons total versus about 6 newtons total originally. So I'd say our model works pretty well. So after that sort of fun interlude, let's go back for a moment to using torque to study rotation and rotational acceleration rather than the maybe more fun application of forces and torques to things that look like architectural structures. So let's use forces and torques to analyze the big red wheel that we first saw in the previous lecture. And let's say the wheel has rotational inertia I, and then let's say the string is wrapped around the wheel at radius r, and there's an object of mass m dangling on the string. For the dangling object, let's write Newton's second law, m a sub y equals the sum of vertical forces acting on this mass. And then for the cylinder, let's write the rotational inertia, which is some, we don't know the value, but let's say it's given to us, times the angular acceleration is the sum of the torques. And let's see what we get. So let's draw a free body diagram for this dangling mass, little m. So here it is, a conventional free body diagram. Let's let the y-axis point upward. So I think we're going to have a downward acceleration. So a sub y we expect to be smaller than 0. We expect a negative a sub y because the acceleration should be downward, and we're going to let the y-axis point upward. So we have an upward force, which is just the tension in the string, and we have a downward force, which is Earth's gravity, and it's also accelerating downward. So Newton's second law would give us m a sub y is up minus down. That's tension minus mg, which gives us tension equals m a sub y plus g, but a sub y is negative, so this is going to be smaller than mg. Now let's draw an extended free body diagram of the wheel to work out the angular acceleration of the wheel. And really, I think the only force that matters is the tension. There is a weight, but the axis of rotation is the axle through the middle of the wheel, so the weight of the wheel doesn't matter. It's going to have 0 lever arm. So I think the only torque that matters is the tension in the string times its lever arm. So writing the rotational inertia of the wheel times the angular acceleration of the wheel is the sum of torques on the wheel is pretty easy. And if we define the rotational acceleration to go clockwise, just because that's the way we drew the picture, then a positive tension should give us a positive torque, should give us a positive angular acceleration. So this is just this tension times the radius. So the only non-zero torque applied to this wheel, neglecting friction, is the string tension, and it has a it's a vertical force, so it has a horizontal lever arm of r. Now, if these two masses out here were not oriented symmetrically, then they could exert a torque. So suppose one of them were in and one of them were out. Then if they were not oriented vertically, then there would be a non-zero torque. They would tend to pull one of them down to the bottom. But because they're oriented symmetrically, whatever torque one of them might exert is canceled out by whatever torque the other one might exert. So that's balanced. So there's really only one torque that interests us. It's the torque exerted by the tension in the string. So then we can plug in this expression for the tension, and we get that this is m times a sub y plus g times this lever arm r. Then, as long as the string is wrapped tightly around the wheel, then every time the string goes down by one circumference, the wheel will go around by one revolution. So we can write, just as we wrote, arc length is r times theta, and we wrote v equals omega r. We can write the magnitude of a sub y equals alpha r, except that we said that a sub y was negative. So if this wheel is accelerating clockwise, which would be positive alpha the way we've drawn it, then the mass is accelerating downward, so we need a minus sign. I think we have a sub y equals minus alpha r. That's because we have v sub y equals minus omega r. So if omega is clockwise, then if the wheel is going around at rotational velocity omega, then the mass is going downward with vertical speed omega r. But since we have our y-axis pointing upward, that would be v sub y equals minus omega r. So a sub y is the rate of change of v sub y, and alpha is the rate of change of omega, so a sub y is minus alpha r. Plugging that in, we get I wheel alpha wheel equals, so tension times r, m a sub y, well a sub y is minus alpha r, and then plus little g times big R. Now we have, and this is the alpha of the wheel. So we have two terms that have alpha, so let's put those together. Dropping the W subscript and just multiplying everything out on the right hand side, we have I times alpha on the left side equals, so this term is a minus sign, minus m, and this other r gets distributed. So we have minus mr squared alpha, and then plus mgr. Then we can move this mr squared alpha term over to the left side to join the other term that has alpha. Now we have alpha isolated, so we can just divide both sides by I plus mr squared. So this is an exact expression for the angular acceleration of the wheel if the wheel has rotational inertia I, which includes the contribution from these big adjustable masses here, and if the thing on the end of the string has mass little m. And we said the first time we used the big red wheel that the tension in the string would just approximately equal mg as long as this acceleration stayed pretty small. And the tension in the string being approximately equal to mg is the same as the statement that this mr squared in the denominator is small compared to this rotational inertia. So if this mass is not too big, and in particular if this mass times this lever arm squared is very small compared to the rotational inertia of the big red wheel, then we just get the angular acceleration as mgr divided by I, which is sort of the approximation we were using in our mind's eye when we first saw the big red wheel, and we were adjusting the radius and adjusting the mass and trying to see how the angular acceleration varied in the different circumstances. So it's often interesting in physics to evaluate limiting cases, and in the limiting case where the acceleration downward of this mass is much, much smaller than little g, then this expression would become just mgr divided by I. And the statement that the downward acceleration of this little block is much less than g is the same as the statement that this rotational inertia of the big wheel is much bigger than this little m times this r squared. So we can ask, why did increasing the dangling mass m increase the wheel's rotational acceleration alpha? Well, it's easy to see in this limiting case. If you increase m, then alpha gets directly bigger. If you don't use that limiting case, then you sort of have to argue that this I is much bigger than this term in the denominator. But as long as we don't make the mass here so big, or as long as we don't make the rotational inertia of the big wheel so small, then this mr squared term should be a lot smaller than this I term, so the angular acceleration alpha should just be pretty close to mgr over I, and then you can directly see that making this mass bigger increases the angular acceleration alpha. Why did increasing the radius r from which the dangling mass was suspended increase the wheel's rotational acceleration? Well, again, you can see this big R here upstairs. So in this limiting case where the rotational inertia of the wheel is much bigger than this mr squared, then you can see that if you make R bigger, then this angular acceleration alpha will be bigger. Why did sliding the big rotating masses farther out on the arms here decrease the wheel's rotational acceleration? Well, you can see if you make this I bigger, and it doesn't really matter in this case whether we have this other term here or not, making this I bigger certainly makes this angular acceleration alpha smaller. But really, when we were working with the big red wheel, we were using this limiting case where alpha is approximately equal to mgr over I. So making m bigger made alpha bigger, making r bigger made alpha bigger, and making I bigger made alpha smaller. So that all makes sense. But to get the answer in a really simple form, it helps to be able to use the approximation that the rotational inertia of this big wheel is much, much larger than this mass times this lever arm squared. Oh, that's really pretty slow.